Welcome to the deep dive. Today we're tackling something requested by you, those pesky zombie processes that can sometimes haunt Docker containers.
That's right. We're going to unpack what they are, why they happen, and most importantly, give you some practical ways to, well, exercise them from your systems.
Perfect. So for anyone maybe newer to this, Docker containers are basically ways to package and run applications in isolated environments. Right?
Exactly. Think little self-contained boxes for your code. But inside those boxes, processes run, and sometimes things don't clean up properly when they're done.
Which leads us to zombies. Okay, it sounds dramatic.
Right.
What exactly is a zombie process in this context?
Yeah. Less brain eating, more resource lingering. Imagine you tell a program to do a small task. It finishes, but it never reports back, hey, I'm done.
Okay.
So technically, it's a child process that is finished running, but its parent process hasn't acknowledged this completion, hasn't collected its exit status.
So it just hangs out, even though it's finished its job.
Precisely. It stays in the system's process table, not really doing anything, but still taking up a slot. Like you said, a ghost process.
A ghost, okay.
Yeah.
Why is this more of a problem, or maybe a different problem, inside Docker containers specifically?
It really comes down to process management, especially PID1. That's the first process started in the container.
Right.
In a normal Linux system, PID1 is usually a special init process that, among other things, adopts and cleans up orphan child processes, including zombies whose direct parents died.
But in Docker?
Often your application itself becomes PID1, and many applications just aren't written to handle that responsibility. They don't expect to have to clean up other processes or handle signals like isccHLD, which indicates a child has terminated.
Ah, okay. So the application, running as PID1, might just ignore finished children because it wasn't designed for that parenting role.
Exactly. The parent process that spawned the child might also be badly written. Maybe it just never calls the wait system call to check on its children. That's the most direct cause.
So either the direct parent doesn't clean up, or the main container process, PID1, isn't acting like a proper init system.
Both can lead to zombies accumulating. The child finishes, sends a signal, but nobody's listening properly to collect that exit status and remove the entry from the process table.
Got it. So how would you even know if you have these lurking around? They sound pretty invisible.
They kind of are, but you can spot them. The classic way is using the ips command inside the container, like PO.
Okay.
You look for processes that have a Z in their status column, Z for zombie.
Simple enough. Anything else? Like, would resource usage spike?
Not usually from the zombie itself. They use almost no memory or CPU, but sometimes the reason you have zombies might correlate with other problems causing resource issues. It's more of a symptom of poor process management, maybe. Checking kernel process stats in the T group could also give clues, but PS is the go-to.
Okay, so PO go Z, basically. Let's say we run that and, oh dear, we see some Z processes. What can we actually do?
Well, ideally, you'd signal the parent process of the zombie. Sending isccHLD might prompt a well-behaved parent to finally reeb its child.
Might, okay. What if that doesn't work or isn't feasible?
Then often the practical solution is, unfortunately, restarting the container. That definitely gets rid of them.
But it doesn't fix the root cause, right? They'll just come back.
Exactly. Restarting is a temporary fix. To really solve it, you need preventative measures.
Right, prevention. That sounds much better. What's the key strategy?
The number one thing, honestly, is using a proper container init system. Tools like tini or dumb-init.
Tini and dumb-init, how do they help?
They are tiny programs designed specifically to run as PID1 in a container. They start your main application, but they also handle signal forwarding correctly and, crucially, they reap any orphan zombie processes.
Ah, so they take on that cleanup job that the application might not be doing.
Precisely. And Docker makes this easy now. You can just add the init flag when you run your container.
Init. Good tip.
Yeah, Docker uses tiny under the hood for that. It's usually the best first step.
Okay, what about things we can do inside our application code?
Oh, definitely. If your application spawns child processes itself, it absolutely should handle the isccHLD signal and have logic to call wait or similar functions to reap its own children properly.
So good application design is key too. Don't create zombie children in the first place.
Right. Thinking about the whole process lifecycle from the start helps a lot. Don't just fire and forget child processes.
Makes sense. Any other angles? Like container configuration?
Well, choosing your entry point or CMD carefully matters. Make sure whatever runs as PID1 is suitable, or use init. Setting up container health checks might indirectly help catch related issues, but it won't directly prevent zombies.
And I guess tools like Kubernetes, do they help?
Orchestrators can help manage the overall container lifecycle, restarting unhealthy ones, but they don't typically reach inside the container to fix PID1 behavior. That init flag or a proper base image is still your best bet at the container level. That's maybe a topic for another time, though.
Right, so stepping back, why should we, the listeners, really care about these zombie processes? They sound small.
Individually, yes, but they still consume a process ID and a slot in the kernel's process table. If you get thousands of them, maybe across many containers on one host, you could actually exhaust process IDs or put unnecessary pressure on the kernel.
Ah, the death by a thousand cuts scenario.
Sort of, yeah. It leads to instability, potential resource leaks, and just general weirdness that's hard to debug. Preventing them keeps your container stable and saves you headaches later. Even a few per container in a really large cluster can add up surprisingly quickly.
Okay, so it really is about proactive hygiene for your containers.
Definitely. The main takeaway is be proactive, use an init system like tini via Docker's init flag. It's such an easy win.
A small change for potentially big stability gains.
Got it. That's the idea. Prevent the problem, don't just react to it.
Great advice. It really makes you wonder, doesn't it? With all the layers in modern software, what other silent performance killers or resource drains might be lurking unnoticed in our systems? Something to chew on.
Always something more to look for.
Indeed. Well, thanks for tuning in to this deep dive.